All right, so just a bit of a random aside here. Let's take a look at the pKa of strong acid. So if you Google the pKa of HCl, for instance, a strong acid, you get a pKa value of negative 6.3. And so if you think about it, it's kind of confusing. So how can you measure the pKa of a strong acid when the dissociation is complete, right? When you have HA completely dissociates into H plus A minus, right? So if we think about the pKa is just the negative log of the Ka. And when you look at the Ka, it's the concentration of the products over that of the reactants, right? But here we have complete dissociation, which means that we don't have any reactants, right? So at the end, we have zero of this, right? And so if the zero goes down into the denominator, right, any number divided by zero is kind of undefined or it's approaching infinity, right? Approaching infinity. So Ka is approaching infinity. So how can you measure a pKa when your Ka is infinite? And so it seems kind of very complicated, but it's actually not that complicated. You just use a different solvent. And so this goes back to the point that all of this stuff is relative. When you say something is an acid or a base, you're talking about relative to something. So in our conversations in Gen Chem, what we're talking about generally is water. So when we say something is an acid, we say it's acting as an acid when you add it to water. When we say something is a base, it's a base when you add it to water. However, what happens when you add two acids together? Which one of them is going to act as an acid and which one is going to act as a base, right? It depends on their strengths. And so what we do is use a different solvent, a less basic solvent or a more acidic solvent. And then we calculate the Ka of the strong acid in that solvent and then make some kind of correlation to predict kind of what it would be in water. And so that's how you end up with these negative pKa. So if something has a negative pKa, it's going to be a strong acid in water.